Hello, my name is Ethan Losasso.
I'm Sara Delawalla.
And I'm Abigail Russ, and we did our project on river flooding and predicting river behaviors through St. Venant's equation. Studying the flooding patterns of riverbeds is an incredibly applicable research topic, as being able to predict when and how rivers may flood and derive the specifics of said flooding will allow for preparation and prevention, saving cities and structures from the damages that intense river flooding may incur. To look at the flooding mechanics, we used two papers in particular, one covering the assumptions and initial conditions and backgrounds of river hydrology, and the other covering the numerical model that we used to base our own numerical model off of. Parameters from both papers are tested, making this project a sort of new and unique look at the whole river flooding modeling issue. So how exactly did we model this? In general, as the title suggests, we based it on St. Venant's equation, specifically using it to create a one-dimensional flow of a dynamic wave. And this wave enters with a linear influx, specifically a triangular influx that increases linearly to a specified peak and then decreases. And we'll go over the initial conditions a little bit later. Getting into the actual derivation, we begin with, guess what? St. Venant's equation for dynamic waves. One specifically, the one for continuity and the one for momentum. And the continuity equation is your pretty standard differential with the partials for the area A and the flow field Q set to be equal and opposite. The momentum equation is a bit more involved, as it relies on values for the slope and friction to define it. The equation essentially sets the time derivative of the time derivative and space of the flow field. The time derivative and space of a flow field to a relationship involving volume, height, and gravity. Below are a more detailed description of all parameters, as well as some defining equations. Height h is not included in this, as our methods will actually, once implemented, sort of redefine it in terms of width and area, rather than its own individual parameter. To find the slope of the energy gradient, SF, we rearranged the Manning equation to solve for it in terms of flow field, area, and hydraulic radius. Then to define hydraulic radius, we used a relationship between area and width as specified below. P is the, what is it? The wet, how do you pronounce that? I'm so sorry. Wetted parameter. Sorry, the text is so small. Wetted parameter. P is the wetted parameter, and we redefine it in terms of things that we can actually work with in the model. So basically, all this is to say, all four of these equations can be manipulated into the form of the advection equation from class, specifically the flux form of the advection equation from class, where it's, some time derivative of some value j combined with a spatial derivative scaled by a factor equal to the fluid velocity, all set equal to the source s of xt. It's further up in the description on our code. And so looking at the equation for radius, we can see that it varies with area A, which then in turn makes the slope of the energy gradient SF also depend on the area A. And so we can rearrange our four equations into the flux form of the advection equation, and we get equation number 5. And you can see alpha and beta are two, once again, defined scaling parameters, and this is the equation that we use to make our numerical model. The final piece, though, before we can actually implement any of the modeling and any of the actual coding, is the initial conditions as specified before. The initial conditions with some time zero constant value of x are pretty simple. We can just set both q and a equal to some constant and move on. Looking, however, at location 0 over all times t, we get into that triangular influx thing where we need to define it throughout different times to create the linear increase and then decrease with some starting value q0 and some peak qp. Overall, this kind of concludes the derivations and the initial setup and the thought behind our numerical model.
Cool. Then for the numerical methods, so to discretize the advection equation, we used the method used in the Celestiono paper, which is similar to the original paper, but it uses an upwind forward Euler scheme, where both time and space are discretized using the forward Euler method, as you can see there. And then so using those equations, we can get a marching equation for Q, which uses information from the current and previous spatial steps to calculate Q at the next time step. And then since alpha and beta are also changing spatially, they need marching equations as well, which you can see there. And then for the marching equation for the cross-sectional area, it uses A and Q at the current and previous spatial steps to find A at the next time step. So to calculate everything more quickly, we used a bidiagonal finite difference matrix for each time step. And then since alpha changes with each spatial step, this matrix had to be created for each spatial step as well. And then we chose this numerical method because it uses known information to predict the next time step, which makes it relatively simple to calculate the behavior of the flood wave.
All right, great. So as we just discussed, those are basically a lot of the background from the paper on what our equations are and what our general methods are going to be. So now we can dive into the code for the methods and what our results are. So this first section of code is basically just setting the parameters based on the Celestiono and Werianto paper from 2017. And then the alpha coefficient is modified to fit a rectangular channel as described in the original paper by Changas and Souza in 2005. And I'll get into all of that in just a second. So first off, in setting our parameters, we have our constants. This is like the gravitational constant, the channel width, which we hold constant, the roughness coefficient, and the bed slope. The channel depth, that's basically an initial value. And when we're setting our initial conditions, we can set our initial flow condition to be 3. Our peak flow condition, which I'll explain in a second, that's more with the boundary conditions, we set that equal to 12. And then we use this initial height we set earlier to define an initial steady state cross-sectional area for the river. Now we can set up more of our spatial and time parameters. So in here, we're just creating a spatial interval size and a final interval. And then we find the number of space steps that we take overall. This will be important for our iteration later in the code. For the time parameters, we have the dt, the interval size, we have the initial time and a final time. And then we again have the number of time steps, which is important for iteration. And so here we're setting the boundary condition peak influx time and base influx time. So this peak influx time is basically where the influx at the mouth of the river is going to equal this max inflow. And then the boundary time is when it returns to that base flow, that Q0 value. Again, this is for the boundary conditions. We'll show that all in just a minute. So before we run on to running the models and actually getting the graphs and everything, I'm going to skip forward to explaining the functions that we use to generate these plots. So this is basically the full model function. This is the meat and potatoes of this project. So here we have all of the initial conditions and parameters that we talked about earlier, basically going into this wave model function. So the first step of this function is to set the initial conditions and initialize the Q matrix in the A matrix. So that's what we're doing here, just creating an n by x by nt matrix. So it's going to be the number of time steps. That's going to be the number of rows in the matrix. And then the number of columns will be, oh, sorry, number of rows is the number of spatial steps. The number of columns is the number of time steps. And this will be the same for A. So now we can go into our main for loop. And this is basically iterating it through each time step. So this first two lines are using separate functions, the alpha calculation function and the beta calculation function, to calculate those alpha and beta values for each spatial step, as we talked about earlier in the explanation of the numerical methods. So I'll scroll down here. Basically, all these functions are doing is exactly that. They're setting up an alpha vector for each time step and then spatially going through and calculating that alpha value at each spatial step. So in the end, this is going to create a vector of those alpha values at each time step for each spatial step. And this beta calculation function does the same exact thing for beta. So it leaves us with these two vectors that are nx long and one-dimensional, so as they are vectors, not matrices. And this can be used to then create our finite difference matrix. So this first finite difference matrix is set up using the SP-diags function. This creates a bidiagonal matrix where the center diagonal is 1 minus dt over dx times alpha vec, and then the back diagonal, so I guess the lower diagonal, is dt over dx times alpha vec. This basically sets up the full version of that marching equation for us, and it accounts for the changing values of alpha through the different spatial steps. And we set the first entry of this matrix equal to 1, and this is accounting for our boundary condition. I'll talk about that again in just 1 second. So here we are creating the finite difference matrix for the cross-sectional area marching equation as well, using similar logic to up here when we created it for the flow field marching equation. Finally, we can use the BC flow function, which is seen right here, to basically formulate our boundary condition. So this boundary condition is time dependent, as we mentioned earlier. This first conditional is just marching it up to that peak value. And then once it reaches that peak value at time TP, it goes back down. And that's basically all that calling this function does. So now we can just run the full model and set this first part of Q to equal that boundary condition. So we ensure that our boundary condition is met, and then propagating the model here based on our marching equations. So in theory, this code should get us to have our solutions for Q and A as time goes on, and we'll show that more here. All right, so I'll run this again real quick just to basically show everything going on. So our first attempt at running the model is going to be using those parameters we set above to plot just the boundary condition to make sure the boundary condition at least works. And this is kind of what that boundary condition looks like. So this is at spatial step 0 and at time, just basically saying what's happening at the beginning of the river as time goes on. So you'll see that the flow rate will increase and increase up until that peak time right here. It's about 12 seconds, sorry. And then it goes back down to reach that initial flow rate at about time equals 25 seconds. So the boundary condition has been correctly applied to the Q matrix. And it does vary a little bit from the paper, but that shouldn't affect the results too much. So when we plot the rest of the conditions, we get a graph that looks something like this. Now, obviously, this is very incorrect based on what the paper's graphs are for both Q, the flow propagation over time, and then also for the area propagation over time. But fear not, we've analyzed this a bit, and we're trying to understand kind of where this error is coming from. So there are a few places where this issue may be arising, and the most likely is the alpha coefficient. So this alpha coefficient relies on both Q and A propagating correctly, and it contributes to the solution significantly more than the beta, which is why it likely messes up the solution so much. So the imaginary component to the solution, which is also, again, certainly incorrect, seems to, again, propagate from within that alpha term. So we can recall the Courant number from earlier in class, and this Courant number basically controls the end behavior of the advection equation and the advection solutions. So when this Courant number is greater than 1, the equation becomes unstable. And if it's less than 1, the equation is stable but diffusive. So in our case, we'd like it to probably be less than 1, just so it does have that slightly diffusive property, as we can see in the papers. But we want it to still not be any greater than 1. Now, the difficulty in this model is because that alpha coefficient is controlling that Courant number, the Courant number can be defined as delta x over delta, or delta t over delta x times that alpha number. And since alpha is changing each time through time and space, it's really difficult to control the Courant number. Like, it's very difficult to keep it under 1, which is probably why the solution is blowing up at a time step of 1. So what we can do to kind of test this theory is pick a time step that's extremely small. So much smaller than 1, we have a time step of 0.3. And once we plot that, we can kind of see that things tend to level out a bit in this time scale. So things become a little bit more diffusive. And in this x equals 200, you can see it doesn't exceed the maximum flow rate that we set as it did before when things absolutely blow up in this plot here. Now, this is a good sign that it does have to do with our alpha coefficient, and it does have to do with that Courant number. The only issue is within the scope of this class and within the scope of our understanding, we don't know how to control that in a way that is able to allow our model to run as it should, as it does in the other papers. So this is not basically within our expectations of the result, but we would like to be able to study that further, possibly in extensions off of this project. So ideally then, we would use the cross-sectional area and the constant width of the channel to calculate the change in wave depth in the channel over time. This is similar to a figure that is shown in Chagas and Souza and is also shown in the other paper as well. And that's kind of the advantage of using a rectangular channel as opposed to a trapezoidal channel, is because it becomes very easy to calculate this height change over time. However, with our data, we did not find it fruitful to do so just because it wouldn't exactly give us much more conclusive results than just showing the area here. Now, finally, we can conclude that although the code doesn't work and produce results as intended, the logic behind the methods is clear. The general form is an advection equation, and the beta term acts as the sink, while the alpha term kind of acts as that Courant number parameter. Both the alpha terms and beta terms are dependent on Q and A, as well as other physical parameters. So the behavior of flood waves through a river canal or just a regular canal, it's largely going to be dependent on the influx of water and the shape of that canal. So we did learn all that from doing this project. Now, assuming the code actually did work correctly, one interesting study that could kind of further this field is varying other terms over time. So kind of as we did for the alpha and beta parameters, we could vary the river roughness coefficient and the slope of the river. And if you do this in a well-defined way and use actual field data, you could model river flood parameters pretty well for actual specific rivers, which could be a very cool application of this project. But that is about it for our notebook. Here are our references here. Again, those two papers that we kept on referencing throughout this project. And I hope you enjoyed the video walkthrough. Thank you.